Today we have Dr. Ramon Lopez to speak to us on magnetospheric currents. Dr. Ramon received his BS in physics in 1980 from the University of Illinois and his PhD in space physics in 1986 from Rice University. He's currently a professor in the Department of Physics at the University of Texas at Arlington, where he leads a research group that works in both space physics and science education. He's also a co-director for the You Teach Arlington Teacher Preparation Program. His current research focuses solar wind magnetosphere coupling, magnetic storms, and the application of research-based pedagogy to upper division and graduate physics courses. Dr. Lopez has authored over 120 peer-reviewed publications, as well as the popular science book, Storms from the Sun. Dr. Lopez has also served on numerous committees of the national academies, such as the Committee of Solar and Space Physics and the 2012 Decadal Survey Steering Committee, as well as the NASA's Living with a Star Program Steering Committee, and other community service roles. Dr. Ramon is active in promoting science education and diversity in science at all levels. He has also served on several scientific and education-related committees. Dr. Lopez has won numerous awards for his work in both space physics and science education. The list is actually very long, but I will definitely quote a couple of them. Those include 2002 APS Nicholson Medal, the 2010 SACNAS Distinguished Scientist Award, the 2012 APS Edward Bosch Award, 2 NASA Group Achievements Awards, and so on and on and on. So the list is really long, and Dr. Lopez is also fellow of the APS, AAAS, that is American Association for the Advancement of Science, and American Association of Physics Teachers, that is AAPT. So we are really lucky to have you, Dr. Ramon. Welcome you again, and now I think you can start the presentation.
Okay, thank you very much for the introduction. I assume that the screen sharing is working and you see my title, Magnetospheric Currents. Now, you could spend not just an hour talking about magnetospheric currents, you could spend a whole week talking about magnetospheric currents. So I'm just going to be hitting a few highlights and my perspective on magnetospheric currents, but try to sweep through the whole domain of the current systems. Now, as far as my perspective on currents in a plasma, I'm definitely on the point of view of magnetic field and velocity of the plasma are the important quantities. You know, at home, I can flip a switch and the lights go on, and the current flows with the typical Ohm's law that you learn in high school, you know, V equals IR. But in space plasmas, because of the scale of the system, the fundamental quantities are really the velocity of the plasma and the magnetic field. The forces on the plasma tell the plasma how to move. And the magnetic field generally is frozen into the plasma, and so the field moves with the plasma. So that is what determines B. And then J is determined from Ampere's law, just taking the curl of B. And the Ohm's law that you generally use is just E plus V cross B is 0. So the electric frame, or the electric field is frame dependent. It just really depends on what is your motion relative to the plasma. And Vytenis Vassiliounis has written extensively on this subject, but there's one very nice paper that that I could refer you to in 2005 on LSG Physiki. So for an isotropic plasma, the MHD momentum equation is rho dV dt is minus the divergence of the pressure tensor plus the J cross B force. And if we assume an isotropic plasma in force balance, then J perp is just B cross grad P over B squared. And this is something that I show students, actually, this particular diagram. How does a pressure gradient, you know, drive a current if nothing's really moving, if the plasma is just sitting there fixed to the field? Well, if I've got a magnetic field, B that points up, and I've got these charges that are moving around in gyro circles around the field, and I've got a gradient in the number of particles, that would be then a gradient in the pressure. You can see that I can just draw a rectangle. And in the first rectangle, I have 3 charges coming out and 2 charges coming in. So that's 1 net charge moving out. And then the same thing for the second rectangle, 2 coming out, 1 going in. So that's a net flow of charge through that surface, and that's a current. And that would be an example of just a pressure gradient driven current. So the first current I'm going to talk about is one that, it's not the oldest one that people had talked about, but certainly it's one that is at the root of space physics, the Chapman Ferraro current. And it was Chapman and Ferraro who in 1931 published in JGR a series of papers on a theory of magnetic storms. And these figures are taken from their papers. And they envisioned a cloud of plasma of equal number of ions and electrons coming from the sun and hitting the magnetic field of the Earth. They really didn't view the solar, something like the solar wind, a continuous outflow, but imagine these episodic clouds coming from the sun. And that would create, the Earth's magnetic field would create a cavity in that cloud, and that stream would envelop the Earth's magnetic field and compress the Earth's magnetic field, giving the sudden storm commencement. And there would be a current that would form along this boundary. And that was the Chapman-Ferraro current, which actually in their papers, they also model it as a image dipole to keep the field of the Earth on one side of the page and then exclude it from the other side of the page. Now, in their drawing of this stream coming past the Earth, they also included some arrows indicating motion of charged particles, because they wanted also to talk about another feature of magnetic storms, which is the ring current, and I'll get to that later. And they envisioned these particles coming around and actually circulating around the Earth and creating a current around the Earth, because by then people understood that there had to be this ring current around the Earth that would produce one of the most important features of magnetic storms. But the current that flows along the boundary is termed the Chapman-Ferraro current, because that's what shields the Earth's field and confines it inside of what we call the magnetosphere. The term magnetosphere, by the way, was coined by Tommy Gold in a JGR paper in 1959. And actually, it turns out that the first use of that word magnetosphere was in a paper that was published in the month of my birth. So I and the term magnetosphere are exactly the same age. So the Chapman-Ferraro current is that boundary current, and by the 1990s, you even had pictures of in encyclopedias. This is from Encyclopedia Britannica in 1990, and drawn for a southward IMF. If we do that, then we've got the solar wind electric field pointing from the dawn to the dusk. And you can imagine these charged particles in the solar wind coming in here towards the Earth, and then they are deflected by the Earth's magnetic field. The ions are deflected this way, the electrons are deflected this way, and that gives you a net electric current across the day side. And if you just put your thumb in the direction of that current, you see that it would produce a negative delta B on the sunward side of the current and a positive delta B on the earthward side of the current. So that reduces the field outside, in fact, removes the dipole field from outside and essentially doubles it on the inside, and confines the Earth's magnetic field to that magnetospheric cavity. And then those current lines are shown as closing along the boundary. Again, the current is going to be consistent with the change in the magnetic field across the boundary. And if you go to the high latitude current or along the upper surface of the magnetosphere in the tail, and you put your thumb in the direction of that current, you see that your fingers are pointing in the direction of the lobe field below the current and then canceling the lobe field above the current. Now, for a dawn to dusk electric field, that Chapman Ferraro current at low latitudes is a load, and it's poleward of the cusp where the current is flowing in the other direction from dusk to dawn, that you have a generator region. And then that Chapman Ferraro current is flowing on closed field lines. So the J cross B force is exerting an outward force on the solar wind. And that was the whole picture, is that you've got this force on the solar wind that is balancing that solar wind pressure. But if we have any kind of southward IMF, actually, the Chapman Ferraro current, that boundary current, if you say it's the entire boundary current that that transitions the field from the magnetosheath to the magnetosphere, it can't all be flowing on closed field lines, because for any southward IMF, there's going to be a small region in the magnetosheath where the magnetic field is transitioning from its southward direction to the northward direction, and we can take the point where BZ crosses 0 as essentially the position of the merging line on the day side and the boundary between open and closed field lines. So even for moderate southward IMF, there's going to be some portion of the Chapman Ferraro current that is flowing external to the magnetosphere. And for very large southward IMF, you could have the magnetic field inside and outside the magnetosphere be essentially equal. Now, we don't normally think about these kinds of cases because the zero order determination of where the magnetopause is to take the solar wind pressure, the rho v squared of the solar wind, and to balance that against the magnetic pressure in the magnetosphere, b squared over 2 mu naught. And in doing so, what you're saying is that, well, the magnetic pressure of the solar wind is not so great, so we can pretty much ignore that. And the plasma pressure inside the magnetosphere is not so great, so we'll ignore that. It's really a balance of the magnetic pressure and the dynamic pressure of the solar wind. But under conditions where the solar wind magnetic field is very, very large, actually the magnetosheath can be magnetically dominated, and the majority pressure in there is the magnetic pressure, not the plasma pressure. And in those kinds of cases, actually at the magnetopause, you can have a situation where you have no net J cross B force on the flow. You've got the internal Chapman Ferraro current, which is giving you an outward J cross B force, but this external Chapman Ferraro current is the J cross B is in the other direction. And the Chapman Ferraro current, that boundary current that is associated with the magnetic shear across the magnetopause, is distributed half and half in the magnetosheath and in the magnetosphere. And here's an example of that was published by myself and Walter Gonzalez a few years ago. It's a Themis crossing, and it happens actually very, very quickly. You can see this very sudden transition in the magnetic field. And the magnetic field actually was a little bit larger out here. Now that's an average of over a couple of minutes out here, but actually what was happening is that the field was getting slightly weaker, and then we hit this transition and enter the magnetosphere. And of course, the satellite is not really moving across the magnetopause. It's the magnetopause that's moving across the satellite, because the satellite is not moving very fast at this position. So what was happening is that the solar wind pressure was weakening slightly, and the magnetopause moved out over the Themis spacecraft. But we have a case where essentially it's a balance of magnetic pressures between the internal pressure of the magnetosphere and the external pressure of the magnetosheath. And the Themis observations show that the plasma pressure inside and outside was about equal, and also relatively negligible. Now, George Sisko, in a series of papers in the early noughts, drew attention to this issue of, well, what's happening if there's no force from the Chapman Ferraro current? What is responsible for force balance with the solar wind? And that's something that I'll return to later in this talk. So moving on from the Chapman Ferraro currents, I want to talk about the region 1 and 2 Birkeland currents, and also the region 0, also called the NBZ Birkeland current system. And the idea of currents coming from space along magnetic fields and going back out goes back to Birkeland, and that's why we call them Birkeland currents. This is a picture from Birkeland's book on the Norwegian Aurora Polaris expedition of 1902-1903. Birkeland himself was quite a fascinating character, and in some ways ahead of his time. I mean, it's very interesting reading his book. I actually have a copy of Birkeland's original book, both volumes 1 and 2, which I obtained from Alex Dessler. And it makes for fascinating reading, what the ideas that he had in there and the range of ideas that he had. But this figure is widely reproduced, showing these currents that were coming in to the upper atmosphere of the Earth and then back out. And you have to remember that this was before the discovery of the ionosphere. Birkeland had already postulated that there might be some kind of ionized layer up there, but it wasn't until later that the so-called heaviside layer, later called the ionosphere, was officially discovered, right? But Birkeland had made observations from ground magnetometers in the polar region and had determined from those observations that there had to be currents of limited extent in the upper atmosphere, and that they had to be coming from space. That was his conclusion. This idea of Birkeland currents was not accepted for a long time, and Alex Dessler has got a couple of really nice articles about this. One is a short article in Science in 1970, which is actually talking about Alfvén and winning the Nobel Prize. And but there's a longer article about Birkeland and his currents, and why the idea of Birkeland currents was resisted for a long time in the book Magnetospheric Currents that was published in 1984. It's an AGU monograph. So these Birkeland currents, the large-scale structure was identified and discussed by Iijima and Patemra, and they were using triad data. It was a polar orbiting Navy satellite. And they identified this large-scale Region 1 and Region 2 current system. They're the ones who named it Region 1 and Region 2. They also identified a higher latitude system that had polarity reversed to Region 1. And this current system would appear during northward IMF. For southward IMF, you saw this other large-scale system. So the Region 1 current is downward on the dawn side and upward on the dusk side. The Region 2 current has got reverse polarity. It's upward on the dawn side and downward on the dusk side. And the NBZ current, or the Region 0 current, has got polarity like Region 2. It's opposite in polarity to Region 1, so the current goes out on the dawn side and in on the dusk side, but it's much more restricted, high latitude, narrow region around the day side. So what is it that drives these currents? Well, it was Dungy who introduced the idea of magnetic merging and reconnection to transfer solar wind tangential stress across the magnetopause. So for southward IMF, you have merging at the low latitude dawn side, and that merging line extends all the way around the dawn side. And the merged magnetic field lines are pulled into the tail. You can see here that the tension force would pull the field and plasma up, and then the solar wind flow is still attached to this field, and it's pulling the field line into the tail. And that tangential stress is transmitted to the ionosphere, causing those merged field lines to be pulled tailward, that is across the polar cap from day to night. And then in the night side, the field comes back to a reconnection region and then snaps back, completing the cycle with flow towards the Earth and then away on the tailward side of the merging region. For northward IMF, the merging region is at high latitudes, poleward of the cusp. So here's the cusp in here. And up here, poleward of the cusp, you've got the anti-parallel field region, but it's a much more restricted region. So it's a narrower geometry where you can have effective merging. And you would get merging on one end, and then this field line would be connected down here. So it's actually being pulled down the tail by the solar wind flow, but that's actually pulling the other hemisphere towards the sun. And also the tension force in the merging region is towards the sun as well. And the newly closed field line is actually on the day side, not on the night side as we have for southward IMF. So the flow produced in the ionosphere will be sunward as a result of the merging. So we can actually see that here. Actually, here's a picture from a paper by Stan Cowley showing this region 1 current generation and the flow across the polar cap from day to night, and then the return flow at lower latitudes. And here we see during a period of strong and extended southward IMF from DMSP, this is a low altitude spacecraft at about 800 kilometers. And what's plotted here is the cross-track flow. The satellite trajectory is this center line here going across the polar cap. And what you see is that across much of the polar cap, the flow is anti-sunward. So that's open field being dragged back into the tail. And that stress is being transmitted to the ionosphere, causing the ionospheric plasma to flow. And then the return flow is at lower latitudes towards the Earth. Now, since the ionosphere plasma is flowing in the frame of reference of the Earth, there's an electric field. And then there's a current associated with that electric field, an ionospheric Peterson current that flows across the polar cap. And again, it's the consequence of the plasma flow. So there's a force on the plasma, causes the plasma to flow across the polar cap. So in the frame of reference of the Earth, I see an electric field across the polar cap. And here's a picture from a paper by Ganushkina and colleagues that they did a very nice review of magnetospheric currents. And that region 1 current is connecting to that high latitude generator region. So you can see this current loop here, and then other current loops that go further back down the tail connecting to other generation regions. Now right here, I've been talking about the merging part of the generation of region 1, but as we'll see, there are other things that generate region 1 polarity current as well, including things like pressure gradients in the tail that I'm really not going to discuss too much, but I will talk about the viscous interaction in a moment. And up here, poleward of the cusp, remember that this is a generator region. So that generator region is connected to the ionospheric load. Now here's the situation for northward IMF. So this is a period of strongly northward IMF and another DMSP overflight of the polar cap. And you see this more restricted region of sunward flow, and then the return flow that is tailward. And this constitutes that Dungy cycle for northward IMF. But then equatorward of that, you see another region of sunward flow. And so what's going on with that? Well, actually, you have this 4-cell convection pattern. You've got the flow that goes in a cell like this and a cell like that, but then also a cell opposite in direction. In fact, a cell of polarity of the region 1 convection cells for southward IMF. And what happens is that it's not just merging that is producing transfer of tangential stress across the magnetopause, because in the same year that Dungy proposed merging, which is at Earth the primary mechanism by which solar wind energy momentum is transferred. In that same year, Axford and Hines proposed a mechanism that's known as the viscous interaction, that plasma in what we now call the low latitude boundary layer would become entrained by the solar wind flow and start to flow tailward and then recirculate back earthward. So that is a transfer of this mechanical stress across the magnetopause and a transfer of that flow energy to the magnetospheric system. And that flow in the boundary layers will drag field and produce Birkeland current and transmit that flow to the ionosphere. So if you just imagine mapping those flow vortices in the low latitude boundary layer to the ionosphere, you get that kind of convection pattern that is at high latitude, it's anti-sunward, so this is the higher latitude, and the lower latitude, closer to the Earth, it is sunward. And that's that kind of region 1 polarity current. So you have those two mechanisms, the NBZ and the viscous interaction operating, and that's why you see a 4-cell convection pattern. For southward IMF, the viscous and the merging patterns are in the same sense of the flow polarity, so they just come together and you only see a 2-cell convection pattern. Now, what about the region 2 currents, which are at lower latitudes from the region 1 currents and have got opposite polarity to the region 1 current, same polarity as region 0, but the reason for that polarity is very different. Now, those are driven by pressure gradients in the inner magnetosphere. And it's particularly visible during storm times when you build up the strong pressures in the inner magnetosphere. And the plasma pressure and the current maximize near the center of the tail. And this is an image from a figure 1 from Brandt et al. 2002 GRL, showing just one of the cases. They have a table of a whole bunch of different cases where they've taken the ENA images and inverted the ENA image to get an estimated plasma pressure and distribution, and here for a couple of different energy ranges. And in this particular one, the plasma pressure peak is in the early morning hours, but if you look at their table of events, they range everywhere from the morning hours to pre-midnight. So generally, somewhere near the center of the tail, you have a maximum in the pressure. And so where that pressure is a maximum, it's also where you have a maximum current in the tail. And so if I've got current across the tail increasing as I move towards the center of the tail, well, there's a divergence of that current. Something has to be feeding that current so it increases. And that's that upward Birkeland current, the region 2 current on the dawn side. And then as the pressure decreases and the current decreases as I move around to the dusk, that divergence is consistent with the current going into the ionosphere on the dusk side, region 2. So again, for southward IMF, you just get a 2-cell convection pattern. The viscous and the merging cells overlap and have the same polarity. For northward IMF, you get this 4-cell convection pattern because the northward IMF merging, the Dungy cycle, is opposite in direction in terms of the flow it produces in the ionosphere. And it's also more restricted to a high latitude region. And then if you've got pressure gradients, substantial pressure gradients in the inner magnetosphere, you would see the region 2 current. And this is a image from the UCAR MedEd Comet program showing the Birkeland current system. This is for southward IMF. And you've got the region 1 coming in on the dawn side, Peterson current closing across the polar cap, and then the dusk side region 1 going out. But you also have got the opposite polarity at lower latitudes of region 2, and they also connect to the region 1 currents through Peterson currents, north-south currents. And then there's Hall current loops that are opposite in direction to the plasma flow. Here are Ampere observations of two such periods. So you can see very clearly what this looks like in real life. Okay, so on the left-hand side here, we got a very strong northward IMF conditions. Actually, BZ is plus 34 nanotesla, which is pretty strongly northward. And you see this very strong, very clear NBZ current system. So it is going out on the dawn side and in on the dusk side. But it also happens that at this period, we have fairly strong solar wind pressure. I mean, the velocity, it's not enormous, but 500 is bigger than the nominal 400 kilometer per second solar wind, but the density is 40 per cubic centimeter. And the viscous interaction depends both on the density and the velocity of the solar wind. Various formulations of that viscous interaction typically have the interaction scaling like the square root of the density and some power of the velocity. And the viscous interaction is very strong in this case because of the very high density. And in fact, you see at lower latitudes, these viscous cells. You see region 1 polarity very clearly equatorward of the NBZ current system. And then equatorward of that, there's really basically nothing. There's no region 2 current here, no organized region 2, because the Dungy cycle for northward IMF does not cause convection up the tail. Remember that the merging and reconnection is closing field on the day side, and the return flow is in the low latitude boundary layer towards the front of the, or away from the front of the magnetosphere. So there's no flow up the tail, up the center of the tail that's generated by merging for northward IMF. Whereas for southward IMF, which we have on the right-hand side, you can see very clearly, first of all, the much more expanded polar cap, because the merging is much more effective and you connect a lot more flux to the solar wind. And you have the very clear region 1 polarity current downward on the dawn side and upward on the dusk side, and the very clear region 2 current equatorward of that. And actually in this case, we were in the main phase of a relatively minor storm, but it shows that that region 2 current is associated with those storm time pressure gradients. Now the crosstail current and the substorm current wedge are related to these currents because, of course, you have to have a current across the center of the tail that gives you the reversal of the field around the center, because lobe field reverses sign across the center of the tail, and it's produced by the pressure gradient that points towards the Earth. And it closes via the boundary currents. Now, as the southward IMF increases, the region 1 currents increase and flux is transferred to the tail lobes. And that means, in fact, that the whole current system has got to increase because, you know, it's essentially a solenoid, right? So the flux in the lobe depends just on the current flowing around in that solenoid. And it's those kinds of conditions that lead to substorms. And another current system which appears during substorms, which is the substorm current wedge. And that's a diversion of a portion of the crosstail current in the near tail along field lines, closing in a limited auroral electrojet, which appears during substorms. And this current has got region 1 polarity, and it appears within areas of previously region 2 polarity current. So it's clearly close to the Earth. And so in that current wedge, you have a relaxation of the dipole field, or as a field to a more dipolar field as that crosstail current is reduced. And here we see observations from GOES spacecraft showing this dipolarization at the time that substorm goes off and AE jumps up a bit. So what drives a substorm? the simple answer is that it's the Dungy cycle for southward IMF. It drives convection up the tail. This convection is adiabatic, so the pressure grows to unsustainable levels. And this was first identified by Erickson and Wolf back in 1980. So something has got to happen. You can't just drive convection into the inner magnetosphere in a steady way in that way, because as the flux tubes move in, since the convection is adiabatic and the flux tube is significantly compressed, the pressure grows to unrealistic values. So something has got to happen. And the resolution to that global instability of convection is eventually reconnection in the tail that gets rid of the excess flux, and this produces the substorm phenomena. And now, of course, there are all kinds of arguments of what's really the trigger. Is it some kind of current instability in the earth tail? Is it reconnection in the tail? It doesn't really matter in that sense, because in the end, what you have to do is you have to get rid of the flux that you piled up in the tail through reconnection. And when the reconnection occurs, you get these bursts of flow. The bursty bulk flows towards the earth, and they break as they come into the inner magnetosphere. And then there's this additional term, you know, when we've got an unsteady situation as opposed to the equilibrium situation, there is a inertial current from that inertial term, and that points in the opposite direction of the crosstail current. And so that reduces the current in a limited region. And so the divergence of that crosstail current is the substorm current wedge. So now the ring current. Again, you know, the story of the ring current actually is one of the oldest stories in space physics, because the fact that there were occasional disturbances in Earth's magnetic field was discovered in 1724 by George Graham. And by the early 19th century, Alexander von Humboldt had already shown that these were worldwide disturbances, and in his enormous oeuvre, Cosmos, he called them magnetic storms. And there was a campaign, the magnetic campaign by Gauss in Europe and others, to set up observatories around the world to try to study this. And by the early 20th century, there was a consensus there had to be some kind of current around the Earth that produced this worldwide depression in the horizontal component around the Earth's magnetic field. And it was an important part of the theory of Chapman and Ferraro, the idea of how you could generate this ring current, although they weren't very specific about the actual motion of these particles, because it really took Alfvén's guiding center approximation and adiabatic invariance to understand how particles move in the ring current and how that ring current is actually formed. But the storms themselves, we know that they're driven by extended periods of strongly southward IMF. And the disturbance storm time index was developed in 1957 to quantify this. What's the average equatorial disturbance field from the ring current? It was shown that this was proportional to the energy content of the ring current, which makes sense because it's a pressure gradient driven current. So pressure is energy per unit volume. And here I show a particular magnetic storm. It's a really big one with SIM-H, which is a 1 minute version of DST that gets down well over 400 nanotesla. And the 3rd of November of, the 20th of November of 2003. And you see this is driven by an enormous southward IMF that was reaching 50 nanotesla in the solar wind with high speed. So you get this main phase of the storm, and then when the BZ starts to recover, then you get the recovery phase of the storm. It was originally thought that that recovery phase was due to just a loss of particles through charge exchange, because it's the particles that make up the ring current. So if the ring current is decreasing, it's that the particles are being lost. Although later it was understood that actually during the main phase, you've got very strong convection, and a lot of these particles are just lost out the front. They go out through the day-side magnetopods. And the origin of the particles was also believed to be this enhanced convection. That enhanced convection would drive plasma in from the tail and energize it through adiabatic conservation of adiabatic invariance, producing the ring current. And also there are additional important features of the ring current, such as the presence of significant amount of oxygen coming from the ionosphere. But there's a problem with this particular picture, because the Burton-et-al. Equation, which really does a good job of modeling the behavior of DST, is based on this idea of, on the right-hand side, you've got what's called the ring current injection rate. If there's no injection and particles are being lost from charge exchange, then the decrease should be exponential in the DST. So if it's not zero, then something must be driving it. So, but the thing is that the ring current injection rate does not saturate as you get to very large driving by the solar wind. But the potential and the convection does saturate. And this was first noted by Russell et al. In a paper where he demonstrated this issue of saturation of the transpolar potential. So that makes us ask, well, what makes the ring current anyway? I mean, in the Rice convection model, it's low PV to the gamma flux tubes that are interchange unstable, and they bring particles into the inner magnetosphere. And those flows are actually associated with the bursty bulk flows from reconnection in the tail. And it's reconnection in the tail that makes these low PV to the gamma flux tubes. So here's a diagram of storm time that you've got steady southward IMF. And so day side merging and night side reconnection will reach an equilibrium. And in fact, it turns out that the flux, the amount of open flux, saturates as well. So as B gets bigger in the solar wind, in this saturated state, the potential doesn't change, the flux of the open polar cap doesn't change, convection doesn't change. But if B gets bigger, this area has got to get smaller. And then that means that this distant reconnection line has got to move closer to the Earth. And that is the answer. That during storms, you get this quasi-reconnection region in the tail that moves closer to the Earth for larger values of BZ. As you're closer to the Earth, you create even lower PV to the gamma flux tubes because the volume per unit magnetic flux is much smaller if you're much closer to the Earth. So they penetrate even deeper into the inner magnetosphere and produce even more acceleration. And so this leads to the dependence of the ring current injection rate on BZ, even though convection has saturated. Because really, the generation of the ring current has little or nothing to do with convection. It's in different physics. It's just that for low values of BZ, both convection and the ring current respond to BZ. But when you move into this saturated state, the separation becomes clear, and it's because of the different physics involved. So far I've discussed all of these different currents that you can see here, the Birkeland currents, the boundary Chapman Ferraro currents, cross-tail current, ring current, etc. But what's missing from this picture? The bow shock current. Because there's a bow shock out in front of the Earth, and as the solar wind moves across the bow shock, the field is compressed. That means that there's a curl of B, therefore there is J. And you can calculate what that J is, where R is the compression ratio across the bow shock. You have this current on the bow shock, and you can calculate what that current is. And that current is producing an outward J cross B force on the solar wind. So actually, it's doing work against the solar wind flow crossing the shock. And that's extracting mechanical energy from the solar wind flow. And that's what's generating the enhanced field and the current on the bow shock. So here's a simulation from LFM, and I've got JY plotted here in color. This is a meridional plane. And what you see is the bow shock here, and blue is generator. So the whole bow shock is always a generator. Now here's the Chapman Ferraro current, the low latitude load, and the high latitude generator region in the Chapman Ferraro current. And the tail current is all a load. But if you go to these conditions of very strong IMF, saturation kind of conditions, the magnetopause load essentially disappears, or generator disappears. There's a little hint of that blue up here. That's the actual magnetopause. This red up here is not the magnetopause. That's actually a load region where the J cross B force is diverting plasma around the boundary and exerting a force on the boundary and putting work into the plasma. But really, for strongly southward IMF, the only place in the system where there's any significant extraction of solar wind mechanical energy is at the bow shock. So where does this current go? Well, simulations show that it connects in part to the Chapman Ferraro current, to the region 1 current. It's actually Joel Fetter in 1999 who first mentioned this particular connection to region 1, but this has been discussed quite a bit by Siebert and Cisco and colleagues and myself and my colleagues. And Cisco in particular has talked about how when the Chapman Ferraro current is not producing any net outward force, as I showed can happen, that force balance is taken up by the bow shock current. And that's consistent with the bow shock current being really the place where solar wind energy is being extracted, and then it has to be transmitted as Poynting flux across the magnetopause to the magnetospheric load. And here's a diagram. This is my best guess of what the closure looks like. There's some that comes in along Birkeland current. There's some that closes through boundary currents. I mean, that external Chapman Ferraro current is one place where bow shock current can close. And that current produces J cross B in the magnetosheath that's in the direction of the solar wind flow. It's reaccelerating the solar wind and moving it around the magnetospheric obstacle. So most of the energy is going back into the solar wind, into the magnetosheath flow. But some of that energy does come in along Birkeland currents and is deposited into the ionosphere. Now, we still don't know a lot of the important details of this, and this picture is certainly subject to revision, but there's been surprisingly little work done on this particular topic. And in fact, to sum it up, the major current systems in the magnetosphere are driven by that interaction between Earth's magnetic field and the solar wind, and it's solar wind energy and momentum that's transferred across the magnetopause. And so really to understand that, you have to understand where is energy being taken out of the solar wind flow and put into the magnetosphere. And it really is the solar wind flow that's the major source of the energy, because of course the ratio of magnetic energy to solar wind mechanical energy is scales like the square of the Mach number. And even for very low Mach number flows of say Mach number of 2, that still means that there's 4 times as much energy in the solar wind flow than in the magnetic field. And for typical Mach numbers of say 8, it's 64 times the energy is in the flow. So understanding where that energy is extracted and how it's transmitted through current systems is a critical part of understanding magnetospheric dynamics. Now, we know a lot about these current systems, but there are plenty of known unknowns, and probably a lot of unknown unknowns as well. And one known unknown are the details of that bow shock current system. It's received relatively little attention. Most diagrams don't even include the bow shock, but it certainly deserves much more attention. So with that, I'll conclude. Thank you very much.
Thank you, Ramon. It was indeed an excellent and very clear presentation. And we have a couple of questions, so I'll just go through them one by one. So first question is from David Seibert. Dave mentions that like you have invoked a viscous interaction in your discussion of the force cell convection. So how do you envision that occurring? Via diffusion or momentum transfer via Kelvin-Helmholtz waves, or by reconnection during northward IMF, poleward of one or both cusps?
Well, the reconnection during northward IMF above the cusp produces the reverse convection cell. But the viscous interaction produces a convection cell that is the same as region 1 for southward IMF. And that's coming from the low latitude boundary layer. And the primary mechanism that people have talked about is Kelvin-Helmholtz as a means of entraining tailward flow on closed field lines in the low latitude boundary layer. Once you do that, then the flow at some point will turn around and reverse, and then you get that convection cycle. And just the flow down the tail in the low latitude boundary layer produces a shear, because one can imagine that the flow is faster, closer to the boundary layer. So there's a shear across the boundary layer, and that shear produces a shear in the field. And if you just figure out, well, what's the curl associated with that, bingo, you get region 1 polarity current coming out of the low latitude boundary layer on the day side and returning on the dust side.
Okay, perfect. Okay, so the next question is from Eric Lund. Eric wants to know that the auroral currents are often observed to be filamentary, and this filamentary nature has important consequences for the magnetosphere ionospheric coupling. Do you have any comments on what causes this filamentation?
Okay, so I chose not to say anything about ionospheric currents because you could have 2 or 3 seminars just on that, and you could have just. Are you guys planning a seminar on the Aurora? Because you could. I mean, you could have just an entire seminar just on that. So I agree. Filamentary currents are extremely important. There's still a lot of debate about what causes them. Do we really understand how you get these things that are only 100 meters across? Not really. So I would say, yes, I agree they're important. And that's one of the known unknowns in magnetospheric currents.
Okay. Okay, so we move on to the next question. The next question is by Elizabeth Antonova. The question is, what do you think about the possibility of region 1 current supported by azimuthal plasma pressure gradients?
Oh, absolutely. And that was one of the topics that I neglected. And actually, Elizabeth Antonova has done quite a bit of work on that particular subject. So if you're interested in learning more about that, just Google E.E. Antonova, go to Google Scholar, and you'll come up with many papers that examine this particular topic. And I did mention this, that there are other sources of region 1, such as azimuthal pressure gradients in the tail, that I really wasn't going to discuss, because even with the limited amount of stuff that I did discuss, I was pretty pressed on time.
Okay, yeah. Okay, great. So we have just one more question. That's from Ankush Bhaskar. And Ankush wants to know what determines the closure and interconnection of various currents.
The closure and interconnection of all of these different currents? Well, there's lots of different factors. Again, something else I have not discussed at all is ionospheric conductance. I mean, that's super important. And there you've got, really significant interhemispheric asymmetries just from dipole tilt and from season. And the fact that in one hemisphere, the northern hemisphere, you have an ocean, and in the other hemisphere, you've got a continent. So, the polar wind patterns are quite different. So there are just a lot of differences between the 2 ionospheres. Now, remember that you've got merging on the day side that's producing that reconnection potential. And the rate at which flux crosses the merging line is identically that reconnection potential. And so it must be the same in both polar caps, and both polar caps identically have the same amount of open flux. So you've got a potential that's imposed across the polar cap, but different conductivities. So you're going to have different kinds of current closure patterns and different amounts of currents flowing in the 2 hemispheres. So there are all kinds of questions and issues related to those current closure, and many of them do deal with issues of interhemispheric asymmetry.
Okay. Yep. Okay, so I guess that's all for the questions. I just had one comment, could you just share all the references to us so that we can just post them online? After that?
Yeah, I put actually very few references into the talk, but those that I put there, I'll make a list and I'll send them to you.
Yeah, that'd be great. Okay,
yeah,
so
that list would be a good place for people to get started in the
right.
topic of magnetospheric currents.
Because you had a couple of references where they were reviews of all these currents, and by Ganushkina.
Yeah, like the Ganushkina et al. That's an excellent paper that I highly recommend.
Yeah, so I guess you can share all the references and then we can post them online.
Yeah.
Yeah, okay. So thank you, Dr. Raman, and it was indeed a great and very clear talk. So I guess we can meet again next week. Next week, we will have Eric Grimes to talk to us on PySpedas. And so looking forward to see you all next week. Have a great week ahead. And thank you again, Dr. Ramon.
Thanks. Bye.
Thank
Bye.
you.